Okay.
I don't mind if you do that. It's fine.
Okay. Well, thank you. I appreciate that. All right. So what you're going to be looking at is this is, by all practical purposes, the hardest block that we have in here. It doesn't mean you shouldn't stop your studying habits and everything else when you get to block 8 and 9, but you still, keep it up for those 2 blocks. You pass this block, you're doing really good. Why? Because there is a ton of information in there. And what we try to do is we try to give you guys the explanations as to why it is that way. Now, you're only responsible for what's called the basic facts, and we try to take you through it and get you to a higher level so you understand when a question pops up, it's like, no, that's the right answer. So that's what we try to do for you guys here. Now, let me pop up my screen. And see if everybody can see me and see Discord and everything else that's in there.
Is this a podcast?
No, this is my own private stream. What I do for you guys.
That's dope. That's dope, sir.
Well, thank you. What we try to do is we try to record everything and then put it on the RF Transmissions YouTube site so you have something to reference. Now, I'm going to be, I think Sergeant Young will be taking you this afternoon, but this is a one-time good deal where we have to mix an instructor. He's helping me out because I got to do some course development stuff. It happens. So he's going to be taking the 1 o'clock session. I record the sessions and put them up on YouTube for your reference, so that way if you're confused about anything, please, by all means, go there first. And if you're still confused, I'm on Discord a lot. I'm normally on about 6 in the morning all the way up to about 7, 8 o'clock at night. I don't want to pass this around too much, but I do play World of Tanks. That's normally after the 6 o'clock rush. So I do have some gaming experience, not like you guys are playing like Fortnite and Battle Royale games and all those other stuff. But what makes this one interesting is you can apply everything that you've learned in this block to your gaming and anything else that you might be doing that has any computer tags to it. So let me extinguish this one, and as soon as I figure out which one I need, there we go. We're going to be looking at the slides in Block 7. We're going to go through 1 Alpha and 1 Bravo today, this morning, and then Sergeant Young's going to take you through 1 Charlie and Delta and also 2 Alpha. Those are very quick objectives to go through. The first 2 are the first one's relatively easy. The second one is where all the signal formats to where we get a lot of questions on. It didn't make any sense for me to stop halfway through it and delay it into the afternoon. Hopefully by the end of this session you'll understand what we're trying to get at, so when you go into the lab on tomorrow, in the NSM lab, you're not completely going, what the heck is this piece of equipment? So hopefully this will help you along. Let's get right to it. Block 7, Unit 1. We're going to look at identifying basic facts about timing and synchronization standards. Just remember, you got to get 70% on the block test. The nice thing about the block test is there are 40 questions. You're going, oh my God, 40 questions. Well, there's a lot of stuff that's in here. I think you have to get 20, you can miss 12. So that's 28 that you have to get in order to pass the class. You have 2 booklets, so to speak. One's a tech manual, the other one is a tech order. They will be given to you for the block test. You will also have electronic or paper C's and D's to reference when you're asked a question. So let's get right to it. So as you well know, we always come up with an AFSC application. You're going to be dealing with something called time. Time of day, timing in multiplexers, routers, any type of SATCOM equipment, and as far as radios are concerned, we do have that timing in there also. And it all has a relationship. So let's take a look at the purpose of timing, time standards, time sources, time coordination, distribution agencies, timing jitter, and network synchronization. So the bottom line for purpose of timing is we need the synchronization for all stages. Nowadays, that's what it's all using, is a time to keep things efficient, is the best way I can think of this. This is an idea. This was a practical application back in, I want to say, early 2000s. That multiplexer was called the FCC 100. This gives you an idea how everything is put together. You have a nipper net, you got a zipper net, and you got a local switchboard. All of that is coming into the multiplexer, as well as phones and other devices such as computers. You'll notice that the zipper net has encryption before it goes in the multiplexer, and you can see that we have encryption after the multiplexer, and then it hits either the wideband piece of equipment or a SATCOM antenna to get it further out there. This is a real scenario that I have had to use and instruct. So even though it's older equipment, all the principles apply. There are time standards. We got apparent time, mean solar time, atomic time, coordinated universal time, and every occasion we do have hammer time. Dun, 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 dun. No? Okay, bad. So the first one up is apparent. This is the basic. This is like a sundial. It is the least accurate, and the reason why it's so inaccurate is because there might be one day out of the year that the sundial is dead on as far as timing is concerned. Remember that you have the Earth rotates. The rotation varies. It wobbles on its axis. You have the seasons where it tilts. You have what they call an oblong orbit around the sun. So this is the least accurate. When we go to mean solar time, this is where things started happening, where we started developing watches. When you go back and if anybody has orders to go to London, England, go visit Big Ben, they should be completed with it in the, I want to say, the next 2 years. So they had to overhaul it because the timing on it, when you compared it to our universal time, was off anywhere between 10 to 20 seconds, and they would have to vary that time on the pendulum. And if you go to the History Channel, you can look it up. Go ahead.
Speaking on time and things of that nature, like, okay, when all these time standards were like first invented, how are they so accurate with time now? Like, how do you know if you're a second off or a minute off with the most accurate time standard or time scale? You know what I'm saying, sir?
Yeah. I'm glad you asked that question because it becomes apparent when we get further into the slideshow here. And we'll go through that, and I'll explain what you just asked, and hopefully it will answer your question. Is that okay? Can you hold off on that for just a few?
Yes, sir.
Okay. Glad you asked the questions. Thank you. Okay, so what we want to take a look at as far as mean solar time, again, this all derived back in England. It also had everything to do with the people who sailed the ocean back in the day. You know, like the Spanish, the Portuguese, the Dutch, the French, and the English. all had to come up with, well, how do I know where I am in the world? And they figured this out and was able to develop some sort of timepiece to keep time, so to speak. And that's where the universal came in, the universal time, because they realized that the earth was round, and they started developing all these latitudes and longitudes. And they finally figured out and said, hey, let's just make Greenwich, England, that prime meridian latitude up and down the Earth's axis there, and use that for 0 to start with time. And of course you have universal time and GMT. GMT is used for Greenwich Mean Time, and that's where it came from. And of course, as history starts going, we have something called atomic time. Remember, you asked about why in the world, how do we keep accurate time? Well, the process is the atomic oscillators are a lot more stable than the mechanical devices that they used back in the 1800s to the 1900s. So when this happened, they developed this international atomic time. And you can see that bottom sentence there, GMT is still the world's time standard. So when we take a look at this, atomic time is based on this 0 meridian. We have something that back in 1972, when they started going a little bit more mainstream and getting everybody on the same time, we have universal, coordinated universal time. Now wait a minute, if you take a look at the way that it spells out, it shouldn't be UTC, it should be CUT. Let me explain. UTC is the French word for coordinated universal time. It's just the nature of how they use it. GMT, we still reference it, but its UTC is actually the world time now. It comes out of the Universal Time and the Timing Administration International. I think it's, yeah, it is. I'd have to go back and look at that acronym. But both of those are what we keep our atomic time on time. Now, when it says countries keep their clocks within plus or minus 1 millisecond of each other, this is where everybody reference to keep accurate time. There are websites out there that can show you the time from this universal time, and we'll go through that here in just a few. There are 24 official time zones. I'm going to show you here in just a sec the place that I go for, which is a lot easier to take a look at than slideshows. Now I do want to point to this time zone, which is 0 meridian, being that 0 latitude, and then you got Zulu time. Now Zulu time and UTC or 0 meridian, they're all interchangeable. We use Zulu to keep missions on time. We use the local time to get everybody in, because Zulu time is where everything is referenced, if you hadn't noticed this. So let's go take a look at our time and date. Let me modify my display here where you can see it. DaytonTime.com. I love this website. We're going to go to the time zone map, and you can see that, let me realign this a little bit. So you can see everything. This time zone map, you can see that in the United States we have Eastern time, we have Central time. You can hover over the dots and it'll tell you exactly what time it is. Tuesday at 9:16 a.m. Central Daylight Time. Here's, Salt Lake City, and then of course California. Then you have Alaskan time, and I think over in here you have Hawaiian time too. So again, I just wanted to point this out. This is where that UTC is referenced on. You can see down here at the bottom it says UTC. You'll notice where this line goes through, and Greenwich London, or United Kingdom, would be where the timing source happened way back when in the 1800s. Now I want to point to you a couple things. You'll notice that like India has these diagonal lines in them. That's because India decided they want to do theirs on half hours. You also have one in Australia. If you pull that map even bigger, it depends on what what time of the season it is, where there'll be this part right here. There's places where it will be on the half hour, and then the others are on the hour. But I want to point to how countries decide that they want a standard time, like China, for instance. China covers approximately 5 different time zones, but they only have one. And that's to keep their country in sync, bye. In sync. Bye. No, never mind. You guys aren't with it this morning, right? But anyway, it just gives you an idea of where you can go out on the internet. Again, timeanddate.com. There's more to this. Let me get back to the home. I like to go here when it comes to eclipses. Like, for example, June 5th and 6th is a lunar eclipse. We're not going to be able to view it because it covers the part of South America, Africa, most of Asia, and part of Europe, along with Australia, Antarctica. So just pretty ingenious way of doing things and trying to view what we need to be. So let's go back to the slideshow. Let me get this back into view here. And blow it up. Okay, so different time zones. You can see way the countries are going to work it, but everybody references it to a different place, or that UTC, as far as timing. Timing sources. This particular paragraph, the easy way to understand this is, I told you guys to be here at 9 o'clock. I use 9 o'clock on my computer. You're going to check your either watches or computers and go, well, gee, my time is different from your time. You might want to glitchy. Okay. Let me try something here. Check 1, 2. Better? Is everybody else having a problem with my voice on there?
No, sir.
Okay.
No, sir, I'm good.
Yeah.
All right. Could be that Discord on your end might be an issue, but sometimes I have my mic volume a little bit too high. So let me try to explain this primary standard and versus a secondary. So I told you to be here at 9 o'clock. I used my computer for the timing. You're going to take and look at my computer and say, oh, he's at 9:20, mine's at 9:21 or 9:19. Well, at that point, my computer is the primary source. Yours is the secondary source. The moment that I go out and I looked at date and time, all of a sudden, dateandtime.com became the primary source. My computer became a secondary source. Now, what you want to do for your primary sources is always try to get the most accurate source available for your primary one. That's what this whole slide means. There are 2 different types of oscillators out there. We have the quartz and the atomic. Let's look at the quartz. Obviously, it is the least accurate. It has the piezoelectric effect. Oh, you got booted from chat. Oh no. It has two factors that limits its accuracy: temperature and aging. Temperature can be controlled. Aging, you just can't prevent it. Now, anybody know how the piezoelectric effect works? No volunteers?
How the what works, sir?
Piezoelectric effect. How it works.
I forgot, but doesn't it have something to do with the vibration of a crystal?
That
I know
is,
that's what.
Yeah.
yep, that is correct. And then what we do is we apply a voltage to it to vibrate it. So yeah,
And like the mechanical movement of a crystal creates electric voltage, I think, something of that nature. I don't know if I got it backwards or something.
Well, the
like
vibration is a frequency that we're going to use to make our time with. And it's going to go through nowadays with the phase lock loop. If you got one of those digital quartz watches, that's what it does. And of course, it has a limited life. So next up, we upgraded. We went to the atomic oscillators. There are two different types, rubidium and cesium. Rubidium is the least accurate, but look at its drift. That's 1 microsecond in 24 hours, but when you get to cesium, it's even less. So cesium is the most accurate if you're looking at the atomic oscillators. I have utilized the rubidium out there in the field, especially with GPS. There are GPS satellites up there still using the rubidiums. They are putting the cesiums in there, and I think they are upgrading the standards to a different atomic clock that's even more accurate than the cesium is. When we look at time coordination, we're looking at distribution agencies. Okay. First, we had that UTC as our reference for everything. Now we got to have an organization that's going to be able to distribute the timing as well as other items that are out there. But the bottom line is they had to come up with a standard and say, well, how many separate events in a day, which is that 86,400 seconds in that day. And the whole idea behind this is to get everybody on one standard. There are 3 distribution agencies. You got BIPM, USNO, and NIST. Let's take a look at each one of them. The International Bureau of Weights and Measurements. Now, again, this is a French organization. It's based in Paris. That's the reason why it's Bureau, International Precisions and Measurements. And the easiest way to think about this is just look at BIPM. It's the easiest way to do it. When we look at this agency, and you can see that there is a website right here on it, you're going to find out not only does it do time, but it's a standard that the world holds, because let's just think about it. A lot of the people are on the metric system, and a whole bunch of people are still on the American system, so to speak, where we have different weights and measurements versus the metric system. I still remember back in the early to mid 70s, they were trying to get everybody on the metric system, but it fell out of favor real quick. I don't know why, but that's one of those things. When you grew up with the way we do things and you try to implement change, sometimes there is some pushback on it. But this agency you can get to, just look up BIPM.org. You're going to see that it is a wealth of information about different measurements, and they hold the standards. They know what a kilogram weighs. They know what a centimeter is going to measure. Same with inches and pounds and so forth and so on. That's where everything is referenced. So if you got some weights that you need to get accurate weights for and make sure that they are the highest precision, you're going to send it to them to verify that it is the correct weight. Next up, we have the U.S. Naval Observatory. It's based in D.C. However, where they keep the time is right down the road a piece at Pensacola Naval Air Station. They hold the time. You do know that the GPS satellites are the sole, we are, Air Force is the sole owner of those GPS satellites. And we keep our time by using the USNO. You'll see that this phone number right here, you can dial it up and it will give you UTC time and it will give you Eastern time. So it just goes to show you can look at this USNO website. This is the phone number that you can get and listen in on the time hack. Now I will caution you, if you call it and it doesn't pick up the first time, try to call it again, it will pick up the second time. We go to NIST. This is the civilian side. You notice that USNO is our Department of Defense or the military side versus NIST, which is the civilian side. NIST was developed a lot longer, or a long time ago compared to USNO, because it's the civilian side. And the reason they did this is to give out the time hacks on these frequencies, which you'll notice that the call signs are WWV, WWVH, and WWVB. These are on the HF frequency dial of 2.5, 5, 10, 15, and 20 megahertz. And you're going, well, why do we have 3 different call signs? Well, WWV is actually the headquarters in DC. It used to be there in Maryland. WWVH is Hawaii. WWVB is in Boulder, Colorado. You call this number up, it will tell you what UTC time is. There's also another frequency up here. It's like 60 kHz. I wouldn't even worry about it. I don't even think you can. We have a radio that would get down that low, but they do have that in Boulder, Colorado. So how can you tell which one is Hawaii and which one's Boulder, Colorado? Yeah, try that again. Boulder, Colorado. When you hear it, well, the male voice is Boulder, Colorado. The female voice is Hawaii, and there's a lot of history behind it. So if you go to the website, the NIST.gov website, look under history, and it will tell you everything that this particular government agency came up with and developed. Now, when it was developed, it was in World War II with the time hack. So that's the reason why they moved it out to Boulder, Colorado, because back in the day, it was nothing to hear of German subs sinking our ships off the coast. And if you didn't know this, there's a sub off the coast of, I think it's New Orleans, but it's down pretty far, that one of our ships here on the coast sank. They didn't know it. They found it about, I want to say about 10 years ago. Little history there. So we have something that we have called timing jitter. And this could be part of your problem with that voice issue there, Van. And also the reason why you got booted is when we have timing jitter, you may have that problem of glitchiness, or let's say you're playing a game, the ping rate just went up. There is nothing I hate worse than playing a game. You're driving along in in a tank, and the next thing you know, your ping rate hits that 999, and you go, what just happened? And you finally get back in the game and realize, well, gee, I forgot to make the turn and ended up in the river, so I drowned. That's what ping rates will do to you at times. There are 2 different types. There are short-term and long-term. It's just enough a glitch to make things miserable if you're playing a game. Let's look at short-term. This one is what they call small amounts, of fading. The easiest way to prevent this is something called Elastic Store. I like to utilize YouTube when you're having some issues with YouTube videos loading. Sometimes an Elastic Store is needed in order to make that happen. Well, they've incorporated it quite well. So most of the times when you go to YouTube, it'll wait till it buffers enough before it will start playing. Sometimes it happens great, and sometimes it doesn't happen very well. Most of the time, it will work. But that's what an Elastic Store is. It's that buffer that you see when you boot up a video. You'll see a pale line go faster than the original line, the darkened line, when it goes and it starts playing the video. That's to keep your video and audio in sync. We have the long-term jitter. This is where we have two clocks that are unsynchronized. What does it mean by two clocks? Well, if you're talking between computer to computer, by using the phase lock loop in there, that's how you're able to get your time in sync with the other computers in time, if you guys like to play ad hoc games. We have 4 different types of network synchronization: pleisiochronous, mutual, master clock, and master slave. We're just going to go through these and just highlight it. I like to call this one the dinosaur. The bottom line is you're in a kind of like your own little world. What do they call that? Not a wide network, but a local area. Intranet. There we go. In other words, you set up 3 or 4 computers. Each one has their different timing source, and sometimes your timing source may not be accurate as the next person, but the whole idea is when you send data between the 2 of you or 3 of you or 4 of you, you have something to hold that data in there so everything can sync back up. This is called pleisiochronous. Next up, we have mutual. This is where all the clocks are averaged to get an idea as to where everybody is in as far as the timing realm. You have something called a master clock. This one was based, and this has a lot of history, based out of England with Big Ben. Again, I encourage you to go visit the YouTube channel. I think it's a history channel on Big Ben. Tells you how they were able to keep Big Ben on UTC time. If this master clock fails, everything fails. And I give you an example of back when I was in high school, everything was timed to the school's clock. It was a master clock. My senior year, that master clock went out. So they literally have to get on the intercom just to tell everybody, hey, it's time to change class. When we get into master slave, it works a little bit different. This one is if the master one goes, someone else is going to take over and be the main time. The DoD uses this because of the multiple places that we have time at. And if you can see the amount of bases we just have in the United States, you will see that it makes sense to have several, because if our enemies ever decide to take out bases, there's always a backup for our timing. So we've gone over purpose of timing, timing standards, timing sources, time coordination, distribution agencies, timing jitter, network synchronization. Did I answer your question there that you had earlier?
Which one, sir?
I think it's the one on the timing sources on how we got accurate.
Yeah.
Because as you can see, we go from a quartz.
Sir, isn't it due like to the oscillation of atoms, or like a crystal as well?
Well, on atomic time, yes, it has everything to do with the oscillation of atoms. It's a lot more accurate versus if you had mechanical or the quartz and vibrating that quartz over a period of time, like you just saw earlier, that aging of a quartz is not very good. It doesn't keep time over a long period of time. The atomic structure. Let me try to go back to the time distribution agencies. I'm not sure if you remember, but it was, I want to say, a year or two ago where everybody started panicking because the BIPM was going to subtract a second on New Year's night. And everybody was freaking out because, oh, they're going to subtract it, they're going to take it away, our time's all going to be messed up. And nothing happened. That agency, because of the accuracy, every once in a while will either add a second, subtract a second, or do nothing, either on the 31st of December or the 30th of June. That's the way they do that. So, and again, I encourage you to go to BIPM and take a look at the history on that too. But that's
So like with that being said, so if they always add a second, subtract a second.
Okay, you faded out or you cut out or something like that.
I said if BIPM always manipulates time, like add a second or subtract a second. So with that being said, like, is time really accurate? Is it really more of like a subjective, arbitrary truth to it? You know what I'm saying, sir? Is it really accurate? Or is that like the most accurate we could get with time? So just curious.
Okay. Well, there is anomalies out there. Remember I told you about our rotation around the sun is an oblong, an elliptical orbit, kind of like an egg shape. We have the tilting of the axis. On occasion, we will have a wobble, and the time is to compensate for what our world does. We have probably the most accurate as far as the atomic time is concerned than we'll ever have. You know, if you were to take a look at that history video, you will see how many seconds Big Ben will differentiate between the UTCs, and it's anywhere between 7 to 10 seconds plus or minus. And it's really weird because they got to either put, now I'm not sure if you know how the monetary standard is for England, but they have, what we have is a penny and a half a penny. They call them pence. So, but they take the old coinage and use it to get the pendulum to swing to get it back on time by referencing UTC. So in this case, Big Ben was built so they could keep the whole English countryside on time, because Big Ben, when you hear those bells go off, they would resonate for miles. So that's how come Big Ben was built, is to keep everybody on time. With our atomic time, we're doing it for the world instead of England. So to answer your question, it compensates for our wobble, elliptical orbit, tilting of the Earth's axis. It's just the nature. That's all I can tell you on that part. We're about as accurate as you can get. I think the last time I took a look at BIPM, they had in the vicinity of about 50 atomic oscillators that they derive time with. And it's all done by phase lock loop, and where all of them get together, and that's the time for the world. That answer your question there, Aaron Robinson?
Yes, sir.
Is there anything else on that one that you'd like to go over?
No, sir.
Okay. Anybody else got a question?
No, sir.
Hi, Miss Lynch.
Hi.
All right, so let's get to the next one. This is where it starts getting hard. We have Block 7, Unit 1, Identify relationship of basic facts, state general principles associated with principles, capabilities, and limitation of multiplexers. I'm going to go through this pretty fast till we get to signaling format, so hang on to your seats there. Bottom line is you're going to deal with multiplexers throughout your Air Force career, whether it's in your house, because a router/modem can be classified as a multiplexer. You will be working on Block 9 multiplexers, so good luck with that. Let's begin. So we're going to look at general multiplexing terms, input data relationships, type of multiplexing, modes of TDM, multiplexing, signaling formats, and that's where the bear becomes, analog to digital conversion, which is the next part. So let's look at terms, analog and digital. If you know one term, the other term is opposite. I like to give 3 words to analog. They're infinite, unlimited, and a word called indiscrete. Indiscrete meaning unlimited or infinite. Look it up. If you know those 3 words, then digital is the opposite, which would be limited, discrete, and finite. Make sense? At least it does for me. So you have analog is infinite, digital is limited. You have bits. You guys were in the block 6. Difference between bit and byte. We're dealing with 1s and 0s for a binary digit. Multiplexing 2 or more users. And that's so you'll notice it says a composite signal or aggregate. And that's what we're going to reference it to.
So, sir, would link aggregation be considered multiplexing when you combine different lines of a network for like redundancy and stuff like that? For network redundancy, is that considered multiplexing, like link aggregation? You know?
Well, I think that is more of switching equipment. Don't get me wrong, I'd have to look this up. So it's called link. What was the name again? Link what?
Aggregation.
No one's asked me that. That's the reason why I'm writing it down. I'll look it up later. I'll give you an answer to that. I'll post it on the chat for you.
Thank you.
You're welcome. Okay, and we're just showing you here a pictorial view of the channels versus the output. This is your aggregate right here. You'll notice that we have combined channel 1, 2, and 3 in this first box and so forth and so on. We have something called sampling, not to be confused with sampling at the buffet at the local casino. So the bottom line for sampling is everything, when you sample, you have X amount of time. And each one of those samples is X amount of time, and they're divided equally between that time. It can be either analog or digital, depending on how everything works. We're looking at frame. Frame consists of a sample from each channel. It is constructed sequentially. What that means is you can see that we have one frame here. That frame started out with channel 1, which is the diagonal lines. We have a solid bar for the channel 2. We have horizontal lines for channel 3. This is one frame. So they've gone through and taken a sample from each one of those sequentially. It doesn't get out of sequence. If it did that, we're in trouble. Next up, we have non-information bits. How do we describe it? Now, I'm not sure if Block 6 talked about overhead. Did they?
I'm not too sure, sir. I don't think so.
Okay. Overhead is non-informational bits. What does that mean? Well, if I'm sending you an 8-bit word, that means not only will you get the 8-bit word, but you got to have a frame to tell it where it went, because whatever channel you're using, it's got to go to that. 2 is, how do I know when it begins and how do I know when it stops? And did I send you 7 bits even though it was an 8-bit word and the last bit was a stuffing bit? So these are non-information bits. They're not part of the intelligence. They're outside of that 8-bit word to tell it where to go, what to do, and how to do it, if that'll give you an idea.
Yes, sir.
Next up, we have bandwidth. It can be used in different modes here. And when I say modes, you're talking like 56K, which is pretty doggone slow. That's old dial-up. 300 to 3 gig, that's bandwidth. It just depends on what you are looking at in the context that is telling you. Okay, are you referencing to frequency? Are you referencing to how much width I can have for a signal? So forth and so on. There's more to it, but this is a generic version of it. We have something called async. This is what your computer uses. It not only does it send, let's just say, 8-bit words, but it also has stop and start bits. That's telling you where the word is starting and where it's going to end at. Now, if you only send let's just say, a 6-bit word, it's going to have that in there too. I'm just hypothetical, okay? So the idea behind async is to identify where the word starts and where the word ends. It's also probably going to come with a framing bit, and depending on the synchronization, there's more to it, and I'll get to that in just a second. Next up is synchronous. The difference between async and synchronous is async varies. For example, if you've got, let's just say, a train depot, and you got enough people here that's got to go in boxcar 1, 4, and 8, and it's a 10 boxcar train. Well, that train knows automatically to only open doors for that one, for 1, 4, and 8. So they don't have to open the rest of them, and it's quicker to load the people on and send it out. With synchronous, you're going to have a 10 boxcar train, and it's going to stop at channel 1, and it's going to stop at channel 2, regardless if there's anybody to fill that boxcar up or not. It is wasted time, so to speak. Now, isochronous is a different story. The way we like to describe isochronous is async with a synchronous rate. In other words, even though I have the flexibility of the stop and start bit in identifying everything, it's where the synchronous rate becomes a problem. Because the synchronous is going to stop for every one of those boxcars with a huge bandwidth for each one of those frames, because everybody's going to have stop and start bits. Everybody might have, if you're not able to fill that up with an 8-bit word, you're going to have stuffing bits. So there's a lot of a waste on that. Now, isochronous does have a purpose, even though I'm starting to see it phase out because there's other more tech-savvy ways to do this without having a large amount of overhead. And ISO used to be where we would have video and audio, and I'm thinking of something called the WSA, which is weapon storage area, where they would show video of what was happening, they would show audio of what was happening, and everything else that's going on out there for sensors and you name it. So this is just to give you an idea on what ISO is. We're not using it as much. Like I said, I'm thinking it's getting ready to be phased out. But we do use synchronous and asynchronous. We have something called frequency division multiplexing. This is basically the early stages of cell phones before they started using TDMA. So FDMA is frequency division multiplexing access versus TDMA, which we're getting into in just a minute. But it gives you an idea of what actually happens. So if I got on my cell phone, hello? Okay. If I got on my cell phone and I was able to get user A frequency and come in here and user A gets demodulated, gets put in the central office. When I went into a different cell site area, user A on that frequency might not be available, so I would get dropped. With TDMA, it's a little bit different. I'm using almost a frequency band, but I'm using a channel within that band. That's what TDMA does, is it looks at everything and says, okay, here's your time slot in here. Instead of having to go, well, you have this frequency, you have it, but over here on cell site, blah, 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 we're all full, so we're going to bump you. This one makes it a little bit easier, so when you go from one cell site to the other, you have access. And as you can see, TDM, this is the basic. You can see we have frames 1, 2, 3, 4. That's because we have all of our channels in there. So one frame gives us the channels. Frame 2, again, you can see how this all relates as far as what goes out. Again, it goes out sequentially. And we're going back over the TDM. Synchronous. When you look at frame bits and time slots, the nice thing is if it is inactive, you get to have more speed, so to speak, to get your stuff in and out. But if not, here's where synchronous comes in. With this, that's my fault. I thought I was on async. Synchronous is when they're assigning time slots. That's that. Bringing your train in, you got 10 boxcars. You may only have people that go in boxcar 1 and 4. The rest of boxcars still is going to take time. Even though you have less bandwidth to deal with, you're going to waste that bandwidth when no one hops on the boxcar. And this is where you can see where channel 1, 2, 3, and 4, A, B, C, D. This is on frame 1, frame 2, we don't have a C, so we're probably going to do some finagling in here as far as time to keep that time vacant, but it's wasted band space there. And as you can see, frame 3, only A, alpha, and delta are in there, so those are 2 boxcars that's not going to be filled. And the last frame, which is only alpha, you have 3 boxcars that are not going to be filled. Whereas async, this is what your computer uses. And when you're on not late at night, but when you guys get on during the daytime and you're trying to watch a video or whatever, it's going to be a problem because the more people that get on it, the longer you're going to have to wait for time to get your data to move back and forth. It is efficient because if no one's on it and you're the only one that decided to get on, the speed is phenomenal at that point. And as you can see, we don't have to do anything as far as the empty box cars. We keep it going quicker and quicker for people that are not on. Async, you can see that we're going to add overhead. Here's your frame bit. And this is also going for synchronous. We'll have a frame bit, but we won't have in synchronous a start and stop bit. With async, it always comes with a start and stop bit to explain where each word is going to be. You'll notice that when we get into frame 2 from the previous slideshow, you don't see Charlie in there. So that's what I mean by about that being flexible. When we look at async transmitted at a synchronous rate, and that's at isochronous, that's where a lot of the overhead comes into play. And you can see that we may have to put in stuffing bits to keep the timing correct. Demultiplexing. The easiest way to understand it, if you can multiplex, you should be able to demultiplex. It doesn't make any sense to multiplex and not be able to demultiplex. So it's the reverse of the order. So if you multiplex and getting that aggregate out, the idea is when you receive that aggregate, Then you're going to have to separate it out. The frame, for your first frame, you're going to look at all your channels and where to place it, and go to the second frame, and so forth and so on. We have signaling formats, where all these multiplexers are going to use some form. Now, why do we go over signaling formats? Well, you're going to see some of these in the NSM when you program it. Pretty cool, huh? There are 3 different types that we go through. You have non-return to zero, return to zero, and CDI. Before I get into this pretty deep, this is where we start getting into, oh crap, this is, kind of unique, so to speak. Is there any questions up until now? I know I went through it fast.
I'm good, sir.
I'm good, sir.
Roger that. Anybody else got a question? Alright, so let's get right to it. Yep, how do you read that number? Left to right, right to left.
Left to right.
Everybody agree?
Yes, sir.
No one's going to dispute that?
It's about lines, multiply to see it is billion, trillion, quadrillion.
Okay,
Nope, that's how you read it.
Van, you cut out and then you came on strong and then you cut out again. So it might be your mic on that one. Alright. So everybody's saying left or right. Wrong. You read it from
Ones, tens, hundreds,
to
thousands,
left.
10,000s, 100,000.
Now, this is the common problem that we have in electronics, because everybody's, when they read, we always read from left to right. But when we start talking about electronics, it actually goes from right to left, and you're going, crap, everybody's drawing this wrong. That is correct. It's just nature. We just can't help it. We read from left to right, but electronics is from right to left when we talk numbers. And that's basically what we're going to do with signaling formats, is we're talking numbers. So that's the reason why I put this up here, is to demonstrate that when you see a sine wave being made, it should be from the right to left. So most of the time you'll see it being drawn from left to right. Okay, everybody gets the understanding. But I just wanted to point that out to you, that when you're looking at real numbers and real data and that, it's always going to be from the right to left. So let's take a look at an 8-bit word. This is how an 8-bit word is going to go. You'll notice that the clock signal here, for one clock cycle, that's going high and then coming low, starts at the right. All of your 8-bit words, notice at the top part here is 1 through 8. 8-bit words are 1, 2, 4, 8, 16, 32, and 64, as well as 128. You're going to see this when we get into PCM too. So that's how we do this. And the reason why I like to do this is because they actually got it right for the next several slides as far as drawing things out. So you have NRZ. This is the first one we're going to do. I'm going to point you to that first sentence. It is the most common format in multiplexers. I've not seen anything else internally to a multiplexer. So let me try to draw this out for you. You have several users that's got to put information into a multiplexer. Well, every one of their devices may have a different signaling format. And then when it gets to the multiplexer is going to change it to NRZ. Now it doesn't really say whether it's neutral or polar, but my guess is it will always be neutral. Why? Because it's internal to the multiplexer. When it gets ready to send it out to the distant multiplexer, it'll probably change it into a different signal format, most likely NRZ or CDI, and you're going to hear that at the end of this. Question? I thought I heard somebody asking a question. Okay. Nope. All right, so what happens with NRZ is the namesake. It does not return to 0 halfway through the clock cycle. Oh, wait a minute. Clock cycle right there. That's one clock cycle. So halfway through the clock cycle, when this goes down to the 0 line, NRZ is not going to return to 0. It's the data format. You have two different types of NRZ. You got neutral and polar. Neutral is from 0 to +5. You'll notice that this sentence right here, it is not self-clocking. What does that mean? It means I got to send the clock cycle with it to get things synced up on the distant end. So that means it's going to be more data included on that aggregate. You can see by our drawing here, I've sent the clock cycle with the data, and what we are doing is we're manipulating to the NRZ the data to the clock. So we have a 0 data. We always start at 0 coming through. We have a 1 piece of data, a logic 1, so it's going to go high to the +5. Notice that our clock cycle halfway through it, nothing happens. When we get to the 1, another logic level 1, nothing changes to include halfway through the clock cycle. We have 3 zeros in a row, so we're going to hit the 0 line, nothing happens halfway through the clock cycle. We get another data of 1 here. Again, it goes to the +5. Nothing happens halfway through the clock cycle, and so forth and so on. So when you get this signaling format, you get the pieces of data along with the clock so you can make sure everything is synced up when it gets to the distant end. This signal is representing the data. That's all we're doing here. Next up, we have NRZ polar. The difference between polar and neutral, one is neutral is 5 volts difference of potential. Polar is 10 volts. Again, polar is not self-clocking. Let's go take a look. You'll notice that it's almost identical to the neutral. The difference is you now have a 10 volt difference of potential. And why is that? Why use polar versus neutral? Well, there are some scenarios where you'll use neutral versus polar, and most of the time when you're using polar, it's because you're talking distance. When you get to the distant end, let's just say it's beyond 1,000 feet, a neutral signal or a neutral NRZ format will not look anything like the data. The computer on the distant end will not be able to determine whether it's a logic data of 1 or 0. Whereas if you put polar in there over that 1,000 feet, then you're going to see a difference of potential because it can determine, because as you go out further, there's this resistance and your voltages start dropping. So as you get more distance, then you start to see something like in this polar scenario, you might see a +4 and a -4, but the distant end can tell the difference between a 1 and a 0 in this case. Halfway through the clock cycle, if this was a RZ signal, it would return halfway through the clock cycle. But this isn't. This is NRZ. It does not return to 0 at any point in the clock stream or data. We looked at RZ versus NRZ. RZ says return to 0 halfway through the clock cycle. We have 4 different types. We got neutral, polar, bipolar, and bipolar with zero suppression. Let's take a look at each one of them. Neutral, as you well can see, it does the same thing as NRZ, except we're doing something halfway through the clock cycle. You'll notice that it also is not self-clocking. You're going, okay, self-clocking means I've got to send my clock signal along with the data to get to the dis and end so it can sync up. Here is the sequence of events here. You can see we have a data of 1. Nothing happens on this line. But the moment that I get a logic level of 1, we're going to go to a +5 halfway through the clock cycle. We're now going to go back down to 0 because that's its namesake, returning to 0 halfway through the clock cycle. We see another logic 1 for our data, and it does the same thing. Zeros, it doesn't really change any until you get to the next one, and it changes halfway through the clock cycle, and so forth and so on. Let's look at polar. This one's a little bit different because 1s are done at +5 and 0s are -5, as opposed to the last couple of signaling formats being all logic 1s are a +5 and 0s are like a -5 or the 0 line. With this one, you'll notice it says self-clocking here. You're going to see this signal represent the clock cycle, so you don't need to send that extra data of the clock cycle to the dis and end. So let's take a look at it. Here is the first clock cycle. You notice we have a data of 0. Well, with our 0 logics, we're going to go to a -5. Halfway through the clock cycle, we're going to go back up to 0, hence the namesake return to 0. With a data of 1, you'll notice that I'm going to go to a +5 and halfway through the clock cycle, back down. And then so forth and so on. Depending on if it's a data of 1 or 0, you'll notice that each time that our clock cycle does something, along with the data, it represents something in that clock cycle. It doesn't emulate it 100%, but it does something halfway through the clock cycle. So it can determine whether it's a 1 or a 0, and it can stay in sync. It is self-clocking. It's the first one of 3 that are self-clocking. RZ bipolar. You're going to see this one described as alternate mark inversion in the NSM manual. And we'll get to that. You'll get to that this afternoon. Bipolar means that I'm going to flip-flop between a +5 and the -5 for logic 1s. 0 is going to be 0. You'll notice it says not self-clocking unless you have something called with 0 suppression. I'll explain that in a little bit. This is a bipolar. Bipolar meaning the opposite of each other. So you can see we have a data of 0. Nothing happens on this line, but when we put in a data of 1, and let me explain something. We always like to go to a high when we're drawing this for our first state. State being the logic. Okay, so we go a high for a 1, halfway through the clock cycle, goes back down. Hence the word return to 0. The next data of 1, here's where the word bipolar comes into play. Bipolar meaning whatever the first one is, the first logical of 1, I'm going to be the opposite of when I see the next logic of 1. And as you can see, it chooses the -5 for the next one. Returns back to 0. We have 3 zeros in a row. We have a 1. It takes a look back, sees that this was a -5. It's going to go to a +5. Same with the next logic of 1. It sees that this one is a +5, so it's going to go -5. Again, alternate mark inversion is the same thing as RZ bipolar. get it alternate mark inversion. In other words, every time we see a 1, it's going to alternate. Now with zero suppression, this is where we see if there are a few zeros in a row, and if it does it, there is a way in the tech manual that tells you whether or not that it tells you where it's going to throw the bit violation is. Well, first of all, you got to figure out what the heck is a bit violation. So let me show you here. This one shows our clock and our data. The data or logic levels, we got the 0 on the first one, it doesn't change. The next one is a 1, and it changes to a high and then back down to 0 halfway through the clock cycle. We have another data of 1. It's going to go to a -5 and then back up where the clock cycle is. You notice we have 4 zeros in a row, and this is where you're going to see in the tech manual, it's going to tell it where that 0 is going to throw a bit violation. So what it's telling you is, in this case, if I have 4 zeros in a row, I need to throw a bit violation at the 4th 0. It'll tell you where to throw those zeros at by putting it or programming it into the NSM. In this case, I have 3 zeros in a row. The 4th 0, it sees it. I'm going to throw a bit violation. So what the heck is a bit violation? It emulates whatever the last known data of 1 is, so it can tell the distant end to sync back up. It sees that this is a bit violation because it should be a high and not a low. That's where it sees it. Now, if this one was a high, then this bit violation would also be a high. So it's going to emulate whatever it sees in the as the last data of 1 to let the distant end know, hey, I got a bit violation here, get back in sync. So you have data. This is what they call self-clocking. Both are called alternate mark inversion, but normally with alternate mark inversion, if it has zero suppression, will come with something like the lines of, well, I think the NSM tech order goes HD8 Z is the way it spells that out. And what that means is on the 8th 0, when it sees 8 0, it will throw a bit violation on the 9th 0. Now, you don't have to know when the bit violations are being thrown. All you need to know is, hey, with zero suppression, it's self-clocking. Next up, we have something called CDI, conditioned die phase. If you were to look this up on Google, you're not going to find this. My suspicion is CDI is a term used in the military, but it's referenced to something called Manchester die phase. You can see that on the Google search. With CDI, it represents the same thing as Manchester die phase. I think there is some differences, but I haven't been able to find them. So just go ahead. Question?
I think that was an echo, sir.
Oh. I think Mrs. Lynch is getting some feedback. I noticed hers is... Miss Lynch, you might want to turn down your speakers a little bit or turn your mic off.
I'm not getting any echo in here.
I see yours launch every time when I start seeing some issues, so...
Okay.
Just mute your mic. That's all you got to do. Okay, while she's doing that, we'll keep going. All right. Conditioned die phase is different than all the other signaling formats. With conditioned diphase, it works off of transitions, not whether or not it's a +5 or a 0. And what this does is logic levels of 1 is going to have 1 transition. Logic 0 is going to have 2 transitions. Now with these, it's going to make this a self-clocking mode. So those are 3 different types of self-clocking modes, and that's the key thing, is knowing what's clocked and what isn't clocked. When things are clocked, they don't have to send along extra information to tell the distant end how to clock things. With self-clocking, it makes it a lot easier to send to the distant end your signaling format, and the distant end knows how to sync it back up. With CDI, again, it's all about the transitions. Ones, there's only 1 transitions. With zeros, there are 2 transitions. You'll notice that little sentence is in phase with the clock somewhere in the clock cycle. As long as the transitions happen in the clock cycle, it knows at the distant end that things are self-clocked. So let's take a look at it. Here's the first clock cycle. You can see we have a data of 0. That means we have 2 transitions. We always draw going to the high first and then back down. There's your 2 transitions within the clock cycle. Now, it is possible that this first transition or second transition may not happen within the clock cycle itself, but it will happen within the 1 complete clock cycle. It's an unusual occurrence, but it does happen. You can see with the data of 1, there's only 1 transition. Here's the second one, logic 1, there's only 1 transition. Then you have a 0, there's 2 different transitions, and so forth and so on when you see the 0s and 1s. Again, CDI is so much more different than the other signaling formats, and it relies off of transitions and not the +5 or the 0. So is there any questions on signaling format?
Just to sort of make sure, when there is 2 transitions within a clock, that's 0, and when there's just simply could be either +5 or 0 volts consistently, it's considered a 1.
So if you take a look at this 1 right here, the first data of 1, it goes to the +5, and when our next data of 1, it goes to 0. So depending on what the transition was from the last will determine whether it goes high or low. It does not rely on a +5 being a 1.
Yes, sir. Thank you, sir.
Sure. Anybody else? No? Okay. Let's look at Nyquist theorem. This guy can be researched. Go to Google. You'll pull up. The gentleman's name is Dr. Nyquist. He's the one that developed this theorem. He's the one that got PCM launched. And after that, it went full bore. Has anybody ever heard of the free program called Audacity?
Yes, sir.
Okay. Has
Yes, sir.
anybody
I've
used
used
it?
it.
Good.
Yes, sir.
Well, you ever notice that when you export it, it has a, I think right now the current one, they updated it, has 3 different levels that you can do. One of them being insane, the other one average, and I can't remember the middle one. But you notice the sample rate on those things? Oh my goodness. And that's when you're doing an MP3. Not the wave loss, but the MP3s. MP3s are a little bit different in the way they formulate the PCM. But Dr. Nyquist started out and said, you know what? We're going to go from analog to digital. How am I going to do it? Well, he came up with this idea that our voices are from 0 to 4,000. Most of our voices are between the 300 to 3K hertz. You might get some that actually speak a vibrato bass, which would be lower than the 300, and also you're going to have somebody with a higher pitched voice that could go beyond the 300. The radios I've dealt with, I've seen Most of them are 300 to 3K. I've seen some as high as 32. I've even seen some as high as 34. There's one out there that actually saw for 36. But you notice it still stays within that 300 to 3K. He said, well, gee, I'll just make it 4K for preventing what's called sideband foldover. And it had everything to do with how the PCM is going to work and the distortion on the dissonant. So he came up with this formula and said 2 times the highest audio frequency will give me samples per second. 8,000 times a second. That's how much they're sampling on this audio waveform. Most of you will probably go, well, that's pretty small. Well, you don't need anything more. You're not a stereo system like on an FM dial. You only need 8,000 because it gives you a replica of what is happening within the radio. Now, you're going to see this. You've already seen this back in the PRIC 150. It's when you're changing that analog to digital, and it does state it in the tech order, if I'm not mistaken. Tech manual, that it is PCM. So let's look at this. We have 3 different steps of PCM. You got sampling, quantizing, and encoding. The first step, sampling, says, hey, I got 8,000 times that I got to sample this analog signal at. Each one of them are going to be equal in that second as far as spacing is concerned, but I'm going to use something called pulse amplitude modulated pulses. In other words, I'm going to take a sample at that pulse, whether it's above the 0 line or below the 0 line. And that's how I'm going to sample it 8,000 times a second. The next one is going to be quantizing. I'm going to assign it a number. And you'll notice that this graph here, we got a plus 127 and a negative 127. You have a 0 line, and it's a representation of that analog signal in a digital format. These are just pulses. You'll notice it assigns a number, and some of them come in between the number. We're going to address this here in just a minute. The first one is something called, how did we get the plus 127 and negative 127? Now, remember that 8-bit word that we talked about earlier?
Yes, sir.
You see, we got 1, 2, 4, 8, 16, 32, 64. And I'm stopping before I get to 128. If you add all of these up, you get 127. Kind of crazy, ain't it? So you have a plus 127 and a negative 127. So get that creative juices going. There are 2 different tables, a uniform and non-uniform table. With a uniform table, it looks like a graph paper. That's the easiest way I can explain it. So think of that graph paper you were using in, let's say, high school or whatever. And each one of these pulses got to be put onto that graph paper because the graph paper is equal in each one of those squares, both left, right, up, and down. But the problem you have is when they fall in between those lines, how do you assign it a number? Well, if it's 4 or less, it rounds down. 5 or more, you round up. They call this a quantization error, and they equate it to distortion. If you have too many, your voice is not going to sound clear. So that's the problem with uniform quantizing, is you get something called quantization errors in it. And that's when it falls in between the lines. So they said, well, how do you combat that? You go to something called non-uniform quantizing. In other words, we have the same amount of lines between 0 and 127 on the positive side and 0 and a negative 127 on the negative side. Okay. If we squash these lines together more where the voice is, we don't have as many quantization errors. It corrects for most of them, doesn't correct for all of them, because you have certain personality voices throughout the world. So again, you are going to have quantization errors, but it's going to correct most of them when you compare it to the uniform quantizing. So now we got all these numbers assigned. How do we make them into the last step, which is encoding? Well, there's 8-bit words, and I shown you earlier that 1 through 64 gives us 127. What's the 8th bit used for? Ah, there it is, the bottom sentence. Remember we looked at a negative 127 and a positive 127? That last 8th bit is going to tell us whether we're above the 0 line or below the 0 line. Now you're good. So each one of those values, if we take a look at this chart, is identified. And look at the word being written here. I got +2, so here's your 1, here's your 2. So I have a data of 1 to give me a 2 on our 8-bit word. You'll notice that a 0 is in the place for going positive. You'll notice on this side, it's a 1, and that's going to give us a negative. Don't ask me why. I'm beginning to think it's an engineer feat to keep things straight. You'd have to ask the engineer on this one for PCM. But you can look through each one of these numbers and get an idea how these numbers relate by knowing that the 8th bit is telling us whether we're positive or negative on the quantizing table. So now we develop the word and we send it out. 8-bit versus 320K. The more you sample, the more processing speed that you're going to have. And with the radio, the primary purpose of a radio is to get the voice to the distant end, so you don't need high quality PCM going there. I don't need to be utilizing my processor for all the voice. So that's the reason why the difference. Now, I grew up in the time frame where CDs just came out, and we were happy to see 8,000 or 8K sample rate, and then it got to 16, and then it got to 32, and so forth and so on. Now, what do you get? You got Audacity with their MP3s with 320K of sampling rate. Redonkulous. So it just gives you an idea how everything has come into play as far as technology is concerned. Let's take a look at frame period. This one means that and this is the sentence that you should use, the time it takes for one frame to occur. Remember back in the earlier slideshows, we were showing you the frame of channels 1 through 4? Well, that's a frame period. Now think of it this way. Most of our standard multiplexers are 24 channels. So we got a frame that is quite large. How do we figure out if we're sampling at 8,000 frames or 8,000 times a second in those frame periods? Well, they mathematically did this, and you can take a look on the slide here. We classified it as a frame period being 1 over the frame periods. So we get that sampling rate in there at 1 over 8,000, and if you figure this out on a calculator, 1 over 8,000 is equal to 0.000125 seconds, which is 125 microseconds. And what has that got to do? Well, that's how long it takes to sample 24 channels at 8,000 times a second. So we go to pulse modulated sample period. This is a time to sample one channel. So we've got a frame period with all the channels to one channel. So how does that work? Well, we put the frame period, which is at 125 microseconds, over the number of channels that's in the multiplexer. Nowadays, they say the standard for the multiplexers is 24 channels. that FCC 100 I showed you at the beginning of the slideshow is only 16 channels. So you got to pay attention to what is a PMSP of this particular multiplexer. It's going to be different than the standard one is. So frame period over the number of channels, it's 125 microseconds over 24 channels, is going to give us 0.00000528 or 5.28 microsamples seconds to sample one channel. Not all 24, one channel. So if you take 24 times 5.28, you should get the 125 microseconds. Checking on the math bit. So there you have it. Is there any questions on PCM, signaling format, frame period, or pulse modulated sample period, because we're at the end of this? Any questions?
No, sir.
Question.
I'm going to need you to go ahead and just repeat everything you just said.
Look at my stream. When I posted.
Can I get a playback on that?
Yeah, can we get a playback, Mr. Mayor?
Sure. Give me about an hour. It'll be up on RF Transmission's YouTube channel. I'll send you the link.
Okay.
By the way, this is Tech Sergeant McCormick and Tech Sergeant McCusker that just hopped in here to listen.
You got our names right.
Well, Big Mac and Little Mac.
Hi, Miss Lynch.
I mean, he could have had a
Okay. So let me, last question. Is there anything that you want me to go over that you didn't get it clearly the first time? No, maybe? Gomez, I
Nothing on
couldn't hear
mine,
you.
sir.
Okay. Again, I recorded this, so I'll put it up on the RF Transmission YouTube channel. I will send this, or I'll put it in your chat for the link, so you have it for reference. Sergeant Young will be your instructor at the 1 p.m. Stream, and he'll give you the background on the NSM, which is everything from 1 Charlie Bravo, 1 Charlie Delta and 2 Alpha to help you along with the NSM that you're going to see tomorrow. And then starting, I think, on Monday and Tuesday, you have telework, which
Tuesday.
Is it Tuesday?
Monday's a holiday, sir. It's Memorial Day.
Oh, yeah, that's right. I forgot about that. So Tuesday and Wednesday, we'll be doing the teleworking for the rest of the information. Any questions? All right.
No, sir.
All right. We'll see you at 1 o'clock. Sergeant Young will be in to help you out. And after that, I'll see you on Tuesday. All right. So signing off. We'll see you afterwards.
Thank you, sir.
You're
Thank you, sir.
welcome.
I feel abandoned like a puppy.
Oh, do you want to go to the instructor chat?
Yeah, we can do that.
All right,
Yes,
let's go to the
please.
instructor chat. Man,
What?
you guys
yeah,
are
man.
quick.
I just scrolled up.
Karmic was going to yell at me for stream sniping you, sir.
Oh yeah, for sure.
Stream sniping.
Oh,
Karmic, that tournament went awesome, man, by the way.